So today we will continue with the two sample test and two sample confidence intervals. Last time we have studied the two sample inference when the sample size is large. So let's have a quick review of the two sample inference when the sample size is large. So remember that when we talk about two sample inference, we want to compare the means of two distinct populations. So there are two populations with respect to the same measurement. Okay, so there are two populations, P1 and P2, and we want to compare their means, mu1 and mu2. And we have sample 1 and sample 2. And with this sample 1 and sample 2, we want to infer the difference between these two means, mu1 minus mu2. So these are some examples for the two sample inference. And set scores of high school A and high school B. So these are two populations. Severity of disease in women and in men. Heights of New Zealanders and heights of Ethiopians. And coefficients of friction after wear of sandpaper A versus sandpaper B. So these are all examples of two sample inference. And this is a notation. So we use N1 to denote the sample size of population 1, the sample size of the sample we collected from population 1, and same for N2. And mu1 and mu2 are two true means. These are the sample means, x1 bar and x2 bar. We use sigma 1 and sigma 2 to denote the true standard deviations. So sigma 1 squared and sigma 2 squared are the true variances. And S1 squared and S2 squares are the sample variances. So last time, this is everything. This is all we did last time. When the sample size is large, so that means both sample size are large, and 1 is greater or equal to 25, and N2 is greater or equal to 25. And when the variances sigma 1 and sigma 2 are known, then this is the test statistic we'll be using. And under these assumptions, H naught is true. Sample 1 points are ID with mean mu and variance sigma 1 squared. And sample 2 points are also ID with mean mu 2 and variance sigma 2 squared. And the two samples are also independent. Not only the data points within each sample are independent, but these two samples are also independent. And under these assumptions, then the test statistic would have a normal distribution, a standard normal distribution. And this is the reference distribution we use. For the test. And the confidence intervals are this. So this is x1 bar minus x2 bar, which is the estimate of mu1 minus mu2. And this is the standard deviation of x1 bar minus x2 bar. A z quantile is used because the reference distribution is standard normal. And again, when it is two-sided, we use 1 minus alpha over 2. And if it is one-sided, we then use 1 minus alpha. If the sigma 1 and the sigma 2 are unknown, then we use the sample standard deviation to replace sigma 1 and sigma 2. So we use S1 and S2 here for the test statistic. And again, the sample size is large. And same assumptions like this one, and z will also be approximately standard normally distributed. So this is guaranteed by CLT, central limit theorem. And these are the confidence intervals. So the only difference is here we replace everything here, sigma 1 and sigma 2, with S1 and S2. Okay. So no matter the variances are known or unknown, the reference distribution is always standard normal distribution. And when you know the variances, you just use the true variances. If that's unknown, you use a sample version. Okay, so today we will learn about the two sample inference for the small sample. So for the one sample inference, when it comes to small sample data, we will use the t distribution in the confidence interval and hypothesis testing. So same here, we will also be using t distribution. So this is a common assumption you need when you do a two sample test. That is, the true variances of these two populations, sigma 1 and sigma 2 squared, are the same. So they are all the same, and they're equal to a number called sigma squared. Assuming they are the same, then we use SP squared, which is called the pooled sample variance, to estimate the sigma squared. So we do not know the true sigma squared, so we need to use something to estimate the sigma squared. Before, if the sigma 1 and sigma 2 are unknown, we use S1 squared and S2 squared to estimate sigma 1 squared and sigma 2 squared, because we know that there are two variances we need to estimate. So S1 squared and S2 squared separately estimate the sigma squared and sigma 2 squared. But now there is only one sigma squared we don't know. So we also use one estimator. We used this SP squared to estimate the sigma squared. And this is the formula for the pooled sample variance. So the denominator is actually n1 minus 1 plus n2 minus 1. So you can see that this SP squared is nothing but a weighted average of S1 squared and S2 squared. And the weights are depending on the sample size in each sample. Then this is our test statistic for the two sample test. In the numerator, it's still the same as before, but there is some difference in the denominator. In the denominator, we use the pooled sample variance. So this is because we assumed that the sigma 1 squared and sigma 2 squared are the same. Recall before we used this, and since they are the same, then we actually have sigma squared. So they are both equal to sigma squared. And this is nothing but the problem is that sigma is unknown here. So we use the pooled sample variance to estimate the unknown sigma. So we use the SP to replace the unknown sigma. And it turns out this test statistic will be a t distribution random variable. Assuming H0 is true, sample 1 points are ID, and there should be a normal distribution with mean mu1 and a variance sigma squared. And sample 2 are also ID, normally distributed with mean mu2 and a variance sigma squared. So the same sigma squared. And sample 1 points and sample 2 points are also independent. So under these assumptions, the distribution, this is the reference distribution, will be a t distribution with degrees freedom n1 plus n2 minus 2. And these are the confidence intervals for mu1 and mu2 under the same assumptions. So we used the pooled version. So this is still the standard deviation of x1 bar minus x2 bar, but we added hat here because it's not a true standard deviation. We used an estimated version with the pooled sample variance. And we use a t quantile. And the degrees freedom nu in the t distribution is n1 plus n2 minus 2. Okay. So let's do an example. We want to compare the spring lifetimes of a kind of spring at two different stress levels. So there are two different stress levels in this experiment. One is 950 and another is 900. And we collected two samples under these two stress levels. Each of them has a sample size of 10. And we use the sample 1 to denote the 900 stress group and sample 2 to denote the 950 stress group. And we know their sample means. What we will do is we need to do a hypothesis test to see if sample 1 springs lasted significantly longer than the sample 2 springs. So that means the alternative is mu1 minus mu2 is greater than 0. And remember that we have some assumptions about the population. We are assuming that the data are normally distributed with equal variances. And to check these two assumptions, normality assumption and homogeneity of the variances assumption, we can use a normal QQ plot. So what we can do is we make a normal QQ plot of both samples on the same plot. And if both look like a straight line and these two lines are almost parallel, then it is plausible that both samples are normally distributed with equal variances. So this is the QQ plot of the springs data. The blue one is the 950 group, and the white dots are the 900 stress group. So we can see that both of them are likely to be normally distributed because the dots are almost around a straight line, and these two straight lines are almost parallel. So we can say that it is very likely that they are normally distributed, and the homogeneity of variances is likely to be true. Okay. So we have the formal hypothesis testing in these following steps. So the first step is again we put our null hypothesis and the alternative hypothesis. The null is that mu1 minus mu2 is 0, and the alternative is that mu1 minus mu2 is greater than 0. So the 900 group lasts longer than the 950 group. The significant level alpha we chose here is 0.05, and we have the test statistic. These are the assumptions. H0 is true. Sample 1 and sample 2 are both RID normally distributed with the same variance. So sample 1 is RID normal mu1 sigma squared, and sample 2 is RID normal mu2 sigma squared. And sample 1 and sample 2 are also independent of each other. Under these assumptions, the test statistic has a reference distribution of T with degree freedom n1 plus n2 minus 2. So n1 plus n2 minus 2 is 18 in this example. And since it is a one-sided test, the alternative is that mu1 minus mu2 is greater than 0. So we will reject we will reject the null hypothesis when the test statistic is greater than this critical value. So this critical value satisfies that the area under the probability to the right of this test statistic is alpha. So we use the 1 minus alpha quantile, because this part is alpha, means the left part is 1 minus alpha. And then we would just need to calculate S1 and S2 and do a weighted average and take a square root. We get the pooled sample standard deviation, which is 38.3. With plugging everything into this formula, this is the observed test statistic. The critical value we chose is 1.73. So the observed test statistic is greater than this critical value, and we can reject H0 and conclude HA. So the last step would be the interpretation of the result in layman's terms. There is enough evidence that now mu1 minus mu2 is greater than 0, so that means the springs last longer if subjected to the 900 stress than if subjected to 950 stress. So here is just interpreting the mu1 minus mu2 is greater than 0 in the context. And we can also construct a 95 two-sided confidence interval for the difference in lifetimes. The quanta I use is T nu, 1 minus alpha over 2. Nu is 18, and 1 minus alpha over 2 is 0.975. So this quanta gives us the number of 2.1. Again, we plug in the standard deviation sample version. We get a confidence interval from 10.8 to 82.8. And the interpretation would be that we are 95% confident that, because that means this difference is between 10.8 to 82.8 with 95% confidence, and mu1 is the 900 stress group, and mu2 is the 950 stress group. So the interpretation will be the spring is subjected to 900 stress lost between these two numbers longer than the spring is subjected to the 950 stress group. Okay, so this is how you interpret the confidence interval for the difference. You say that one group is between number one and number two longer than another group for this example. And let's do another example. So this example is not to see if there's any difference. So suppose that mu1 and mu2 are the two true means of the stopping distances. Okay, and we use a car driving at a speed of 50 miles per hour and equipped with two different types of braking systems. So system 1 is associated with mu1 and system 2 is associated with mu2. And we collected 6 observations for each group. And we also calculated the x1 bar and x2 bar, the sample means, and s1 and s2, the sample standard deviations. The test is to test at a significance level of 0.01 if mu1 minus mu2 is less than -10. Okay, so this is to test whether the system 1 gives us a mean less than system 2 by 10. Okay. Okay, so this is the interpretation of the alternative, and then we can also construct a confidence interval. So we want to construct a two-sided 99% confidence interval for the two difference in the stopping distances. And this is what we would do. These are our hypotheses. And the significance level alpha we use here is 0.01. The test statistic is this. -10 is corresponding to our hypothesis. And with the same assumptions, under these assumptions, the test statistic would be normally distributed, and 1 plus n to minus 2 is 10. So this reference distribution is the t distribution with degrees of freedom 10. And since the alternative hypothesis is mu1 minus mu2 is less than minus 2. So this is the same as mu1 minus mu2 minus negative 10 is less than 0. That means we will reject the null hypothesis when the test statistic is less than this critical value, where the area under the curve or the probability to the left of the critical value is alpha. That means we use the alpha quantile of the t distribution with degrees of freedom 10, t10 alpha. And we plug in S1, S2, we get the pooled sample standard deviation 5.23, and we plug in the sample mean and the pooled sample standard deviation. We get a test statistic. The observed test statistic is negative 1.19, and the critical value is negative 2.76. So when you compare the observed t and the critical value, you find that the observed one is not smaller than the critical value. And we fail to reject H0 in favor of HA. So this is we should fail to reject H0. There is a mistake. And the conclusion is that there's not enough evidence that the stopping difference of braking system 1 are less than that of system 2 by over 10 meters. Okay. This is just our interpretation of the alternative hypothesis. And the 99% two-sided confidence interval is almost the same as before. So we just plug in x1 bar minus x2 bar, and we also plug in the sample version of the standard deviation of x1 bar minus x2 bar. And the quantile is t10, 1 minus alpha over 2 is 0.995. So that is 3.17. And we get a sample, we get a two-sided 99% confidence interval from negative 23.17 to negative 4.03. Okay. So you may find that in this confidence interval we don't have 0, right? So that means if you do such hypothesis testing, then you can you can reject the null hypothesis and conclude that mu1 and mu2 are different at the significance level of alpha equals 0.01. And to interpret the confidence interval, it's the same. We are 99% confident that because now mu1 minus mu2 is negative. So CI, confidence interval of mu1 minus mu2 are so the two ends are both negative, so that means mu1 minus mu2 is less than 0. The breaking distance for system 1 is smaller than that of system 2. So the interpretation would be that we're 99% confident that the true mean stopping distance of breaking system 1 is between 4.03 and 23.17 less than that of breaking system 2. Okay. So we use system 1 less than system 2 because these two values are negative. Okay, so that is when we have an assumption that these two populations have equal variances. And that is the most common assumption when you do the two-sample t-test. But sometimes you also want to do a test for a small sample when that assumptions cannot hold. Okay. When sigma 1 squared and sigma 2 squared are not the same. So if they are not the same, and of course they are also unknown, then we can use this test statistic. So it's the same. The format is the same as the large sample case, but because we have small sample size, so we cannot use the central limit theorem to get a normal distribution. Therefore, we need some extra assumptions. So the extra assumptions is that they are normally distributed. Okay, so these are the assumptions. H naught is true, and sample 1 observations are ID with normal distribution with mean mu1 and sigma 1 squared, and sample 2 observations are ID with normal distribution mu2 and sigma 2 squared. And this test statistic has approximate t distribution with degrees freedom nu hat. And the degrees freedom is estimated by this formula. So this formula is a special case of cocurrent status White approximation for the linear combination of the mean squared, for the linear combination of mean squares. Okay, so this formula is sometimes also called the cocurrent status wide approximation. And you can also construct the confidence intervals. So everything are the same. We still have the x1 bar minus x2 bar and the standard deviation. So this is also a sample version of the standard deviation of x1 bar and x2 minus x2 bar. And in the quantile, we again used the t distribution, but now the degrees freedom is nu hat. So before we used n1 plus n2 minus 2, right? And okay, and so we can do the springs example again, assuming that the homogeneity of variances assumption does not hold. So although we have already checked that according to the normal QQ plot before, we have checked both samples are normal and the variances are the same. We have checked the QQ plots by, so we have two QQ plots on the same plot, and we have checked that they are almost a straight line, and these straight lines are almost parallel for these springs example. So these assumptions is quite plausible, and but we find that the standard deviation, the sample version, are not actually very close. Okay, so you can also assume that sigma 1 and sigma 2 are not the same. So that means you just you relax the assumption and say that sigma 1 and sigma 2 are not necessarily the same. We only need the normality assumption for that data. And we redo the hypothesis test. So the first thing is that we calculated the cocurrent status white approximation. So the approximately degrees freedom is 14.3. And then we do the hypothesis test. So the null is that mu1 minus mu2 is 0, and alternative is that mu1 minus mu2 is greater than 0. We use the significance level alpha of 0.05, and this is the test statistic. Assuming H0 is true and sample 1 and sample 2 are normal mu1 sigma squared and normal mu2 sigma 2 squared, and these two samples are independent. And under these assumptions, so note that we don't have a common sigma here now. So under these assumptions, the test statistic would be approximately normal, and the degree freedom is 14.3. And we will reject H0 if T is greater than a critical value, because this is our alternative. The alternative is mu1 minus mu2 greater than 0. Okay, then we plug in everything, x1 bar x2 bar and s1 s2, and we get 2.22. The critical value, T, 14.3, and 1 minus alpha is 1 minus 0.05, 0.95, and we get 1.76. So this value, so a T distribution, when you want to get degrees freedom like this 14.3, there is a decimal place. You need to use a calculator or some software like R or MATLAB to get this value. So because in the table you can only find the T quantile when the degree freedom are integers. So for the T table, we only have integer degrees freedoms. So if you use a T table, then you need to round it down to 14 and find the corresponding 1 minus alpha quantile. Okay, so since now the observed test statistic is greater than the critical value, then we can reject H0 in favor of HA. Okay, and we say that if we relax this option, where we don't assume that the variances are the same, we can still have enough evidence to conclude that the springs subjected to 900 stress last longer. So mu1 minus mu2 is greater than 0. It lasts longer than those springs subjected to the 950 stress. And we can construct a 95% confidence interval. So we plug in the sample means and the standard deviations. And in the quantile, we again used the T distribution with degrees freedom 14.3. And because it's a 95% confidence interval, the quantile used here is 0.975. So that is 2.14. And plugging everything to the formula, we have 1.67 to 91.9. Okay. So the interpretation is that we are 95% confident that the springs subject to the 900 stress mu1 last between these two numbers cycles longer because it's positive values longer than the spring subject to the 950 stress group. Okay, this is another example when we obviously have different variances. So this one is comparing the void volume of two kinds of fabrics. So the void volume is measured by the thing called permeability. And these are two types of fabrics we are comparing. One is cotton and one is triacetate. And the sample size for both are 10. And the sample standard deviation for cotton is 0.79, and the sample standard deviation for triacetate is 3.59. So they are obviously very different. They differ too much. And in this case, we will be using the Cochran-Cedros-White approximation to do the t-test. We will use sample 1 to denote the triacetate fabric and sample 2 to denote the cotton. Use the significance level alpha equals 0.05. We want to verify the claim that triacetate fabrics, mu1, are more permeable than the cotton fabrics on average. Okay? And then it means the HA is mu1 is more permeable, so mu1 minus mu2 is greater than 0. And we want to construct and interpret a two-sided 95% confidence interval for the two difference in the mean permeability. Okay. So the first thing is that we calculated A1, N2, X1 bar, X2 bar, S1, S2, and then we have approximate decrease freedom using that formula. So there is a degrees freedom of 9.87. Again, if you want to evaluate the quantile of the t-distribution of degrees freedom with decimal places, you have to use the calculator or the computer software. But if you want to use a t-table in the appendix of the book, then you need to run it down to nu equals 9. Okay. This is to avoid unnecessary false positives. Okay, so these are formal steps of the hypothesis testing. The rule is that mu1 minus mu2 is 0, and the alternative is that mu1 minus mu2 is greater than 0. The significance level alpha is 0.05, and this is the test statistic. And we have the assumption that H0 is true. And for the sample 1 group, the observations are ID normal with mu1 and sigma 1 squared. And for the sample 2 group, the observations are ID with mu2 and sigma 2 squared. And the two samples are independent of each other. And under these assumptions, we will have a reference distribution of t with degrees freer than 9.87. And since the alternative is that mu1 minus mu2 is greater than 0, then we will reject the null when the test statistic is greater than a critical value. So this is a quantile, 1 minus alpha quantile, because we want the probability to the right of the critical value is alpha. And so here we did not use a normal K-plot to check the normal assumptions. But if you have the complete data, you still need to check the assumptions. Because now we don't have the complete data, we only have x1 bar, x2 bar, and s1, s2. So we're just assuming that they are true. Okay, then we plug in the data. The observed test statistic is 72.63. And the critical value, t of 9.87, and 1 minus alpha here is 0.95. Is replaced by T9 of 1 minus alpha, because if you use the T table, okay, you need to round it down, and the 0.95 quantile of T9 is 1.83, and we can see that the test statistic is bigger than the critical value, and we can reject H0 in this case. In the layman's terms, interpretation is that there's overwhelming evidence or significant evidence or enough evidence to conclude that the triancylate fabrics, so this is mu1, are more permeable than the cotton fabrics. Okay. Again, we are just translate the alternative hypothesis according to the context. And to construct the 95 two-sided confidence interval, we'll be using, again, the 1 minus alpha over 2 quantile of T nu hat. And again, we used 9 to replace 9.87. And 1 minus alpha over 2 is 0.975. So that gives us a quantile of 2.26. This is a quantile used in the two-sided confidence interval. By plugging the x1 bar, x2 bar, and s1, s2, and also the quantile, we get 95 two-sided confidence interval of 81.8 to 87.06. So we are 95% confident that the permeability of the triacylate fabric exceeds that of the cotton fabric because they are all positive. So we say that the mean permeability of triacylate fabric exceeds that of cotton fabric by anywhere between 81.8 and 87.06. Okay. So that is the two-sample inference for small sample size. That is all for this video.